my second talk, I will talk more about the lakehouse aspects of HeatWave. So yeah, let's get started. So the motivation for HeatWave Lakehouse is the massive amounts of unstructured data that are available to enterprises, right? So the OLTP, think of it as the top of the iceberg, but under the iceberg we have, of course, analytic databases where OLAP queries are run. But even below that, we have unstructured data where machine learning is going to be important, data lake application is going to be important, and maybe we want to even run queries that combine this information from unstructured data with the OLTP data or OLAP data. Right? So this is motivation, and we want to enable a system where data processing on this large amount of data is possible and feasible. So this is the motivation for HeatWave Lakehouse. So the architecture is very similar. So we have again a MySQL database connected to HeatWave cluster, and now we have the capability of ingesting data into the HeatWave cluster from object store. And the object store has data that has different formats. So for instance, you might have CSV files, you might have Parquet, Avro files, or exports from other databases. And now we are adding capability of ingesting this to HeatWave. So a couple of innovations are necessary, of course. One is on the MySQL side. So we are introducing this concept of an external table. So the external table means data will not reside in any MySQL storage engine, such as InnoDB, whereas it will exist in a new primary engine called the Lakehouse. So we are adding another primary engine. And of course, while ingesting this data, loading this data, we have to define a schema as well for this data. So this can be either driven by the user, or we are also providing automatic schema inference capabilities. So we have the concept of looking at your data and infer a schema, and then use that schema when we are creating these external tables. On the HeatWave side, or the ingestion side, of course, we need a fast and scalable data ingestion from object store, so that this doesn't become a bottleneck. While loading the data, we need to collect statistics from this data so that we can use them at query processing. Because this is something that happens at InnoDB side. When we load InnoDB tables to HeatWave, we collect a bunch of statistics. And the same thing needs to happen as well now while ingesting unstructured data. And of course, query processing becomes more challenging because the scales that we are talking about has increased, right? So now, instead of working on InnoDB scale where we have, let's say, tens of terabytes, now we have hundreds of terabytes of data that we can ingest. And there are challenges associated with that. So I will talk about these challenges and some of the solutions that we came up with. So let me talk about Lakehouse end-to-end flow, workflow. So first of all, we create the table with primary engine as Lakehouse. And this can, auto-provisioning can help here to decide how many nodes you need, depending on your data size. And auto-schema inference, as I mentioned, can help you define your schema. And then in the engine attribute, we have a JSON saying where the files are located, what are the files that we would like to ingest, and what is the format of those files. So if you have a CSV, you can specify different delimiters, new lines, etc. When this is done, we can load the table with this command, alter table secondary load. And as you can see, we can load Lakehouse tables, we can load also InnoDB tables. So that is the warehouse side. And we can run queries now, both that are, we can run queries on tables, both from InnoDB and Lakehouse. So we can mix and match, basically. And this gives you the Lakehouse architecture. You have the capability of running queries on your OLTP data together with your unstructured data.
You mean you can join them?
Yes, you can join them. Yeah. So the ingestion engine we call heat pump. So heat pump should achieve scalable and high performance ingestion, right? So how do we do that? So a couple of ideas here. So instead of doing file-wise distribution to our nodes, so let's say we assign certain files to certain nodes, and the ingestion works in that way. The parallelism is achieved in that way. This is not very robust because there might be file size differences, different data properties that need more processing time, etc. So we need a custom distribution scheme to ensure robust performance regardless of what is being ingested. And for that, what we do is we create tasks, so-called tasks, and each task is around tens of megabytes of data to process. And the task will be done by a thread, a worker thread, right? And then we have batches of these multiple tasks, and these batches are tens of tasks. So in total, each batch will contain around 100 megabytes of data to process. And a task looks like this. So it might have like multiple files, and each file has, of course, its name, then its size, and the offset where we start, where we should start processing, and how much we should process. So this is one task, and then we have multiples of these tasks. And we dynamically distribute these tasks to all the HeatWave nodes available for ingestion. So it looks kind of like this, right? So we have, let's say, B batches of K tasks each, and the MySQL has HeatWave plugin. The HeatWave plugin is doing this dynamic distribution across all the HeatWave nodes that we have, and we get good parallelism. We aim to achieve good parallelism via doing this dynamic distribution. And you might note that number K is much larger than the cores in the single node, and number B needs to be much larger than the nodes in the cluster to achieve robust performance.
So all this process happens when you do a create external table?
No, this happens when we do alter table secondary load. So,
okay.
Yeah.
So you have to form to load the data.
Right. So,
and then you load.
yes. So the external table creation, think of it like the schema definition, and the load happens when we do the secondary load.
Alright. That.
So let's have a look at what happens in each individual HeatWave node while doing this ingestion. So the first step is it gets the batch of tasks from the HeatWave plugin. The second step, we have two buckets here, right, in the object store. One is the user bucket, where the raw data is located. And the second bucket is our internal bucket. So this bucket, the internal bucket, is not visible to the user. So the second step is these tasks that the plugin sends, they actually do not contain detailed information. The detailed information will be fetched from the internal bucket, right? So the node reads the task files. The third step then is reading the actual data files from the object store where the user files are located. So user's bucket. We process data, create partitions, turn this for raw data into HeatWave format, and finally, in the final fifth step, we write HeatWave partitions to our internal bucket. So all the user data has been ingested that way to HeatWave format. Now, if your cluster, let's say, goes down, one node crashes, or maybe the user shuts it down, we have the capability of recovering these partitions from the internal bucket. We do not have to repeat this ingestion process again, and that is much faster. So this is how the ingestion works. And of course, there are more subtleties here that I did not touch upon, but via this massive parallelism mainly, we achieve really good performance. So if you look at our ingestion performance, we can load 500 terabytes TPCH data in 4.4 hours. This is like 2x slower, 2x faster compared to Snowflake, 6x faster compared to Databricks. We are much faster than Google BigQuery and Amazon Redshift in terms of ingestion performance. So this is the ingestion story, right? So now we have data available in our nodes, everything is in memory. How do we again run queries in that scale? So what are the challenges? So scaling relational processing to thousands of cores. So here I would like to, the optimizations that I mentioned in my previous talk are valid here as well. Now I will talk about some other more detailed optimizations that we had to do specifically for the Lakehouse project. As we were developing this, we have faced issues that we have not been seeing in the warehouse scale. So these are the optimizations that we have done specifically to achieve efficiency in the Lakehouse scale. So the first one is something called an adaptive execution. So I mentioned that in our physical compilation, we make some decisions, right? So we, for instance, decide on the join pattern, we decide on the group by pattern. These decisions sometimes turn out to be bad because we have, let's say, bad statistics, or we haven't seen this type of query before. It's especially valid in case of like ad hoc workloads where users write many new queries. So when this happens in the Lakehouse scale, there is a much higher chance of going out of memory, for instance, or not performing well because it's such a large scale. And this has been seen especially in our group by operator, for instance. So let me give you a brief idea of how our group by operator works. So in the group by, we build a hash table on the input partition, right? So this is our input partition. We have, let's say, a key, 2 attributes. Now we build a hash table. Whenever there is a collision on the hash table, or it becomes full, we do a so-called spill. So what we do is we reject that data. We say, okay, spill it back to our input. We will handle it later, right? So we consume as much as possible. And then at the end, we do the aggregation and produce some result. Now we move on to the next cycle. Again, we consume from the input partition. And again, if we need to, we do spill until the input has been completely processed. So the inefficiency here, as you can see, is how much we spill, right? And what is the factor that says how much we spill? So we spill more if the hash table size is configured inappropriately, right? So if we say the hash table is small because maybe we have a low NDB group by, and it turns out it's not the case at runtime, we face lots of collisions and we will spill a lot. So there is the other side of the coin. If the hash table is too large, then we also will face performance degradation because we will not be cache local, right? So there will be lots of cache misses. And also, if the hash table is too large, memory consumption becomes a problem. So there's the trade-off, as you can see, right? The hash table size needs to be really adjusted to provide a good performance, to avoid the spill, etc. So what is the information that we need to size the hash table correctly? The information is actually the cardinality of the group by. How many rows, how many groups we have in the group by, right? So the question that we are trying to answer is, can we get this information at runtime so that we can size our hash table correctly? And the way we achieve this is doing cardinality estimation at runtime with a nice algorithm called hyperlog. So let me give you an intuition about how this algorithm works. It's a very neat algorithm. So the main intuition is, imagine you have a set of values, right? And you hash those values with a uniform hash. So, and then you look at these hashes. So the in each hash value, the maximum number of leading zeros is going to be remembered, right? So you look at your n values, n hash values, and you remember what was the maximum number of zeros, leading zeros, that I have seen in all those hash values. And that numbers you can actually use to estimate cardinality. So let me give an example, then it will become clear. Let's say you have set 1, right? You have numbers 0, 1, 0, 1, 0, 1, 0, 1. What is the cardinality? 2. So you have 2 distinct values. And in fact, if you look at these values, you see the max number of leading 0 is 1, because you have 0, where the leading number of zeros is 1, and you have 1 where you don't have any zeros. So you can use that number to estimate cardinality as 2, which turns out to be perfect. And in the set 2, you have, let's say, numbers 0 to 128. In this case, max leading number of zeros is 7 from 128. And again, you can use that number to achieve perfect cardinality. Of course, these are toy examples, as you can see, so it works perfectly, but in reality, this is not the case. So the disadvantage of this algorithm is the estimate is only in powers of 2, which is not good, which is not practical, and the variance of estimate is very high. Let's say you have a set where you have only 128, cardinality is going to become, of course, 1, but your estimation will say it's 128, which is not correct. Yeah?
What was the name of this algorithm?
Hyperlog. But this is not the entire algorithm, so this is just to give you the intuition. Now the algorithm does something smart about it, about this problem. The algorithm actually does an average, right? So instead of calculating one cardinality, it uses some part of the hash to say, to determine a bucket. And there are multiple buckets. And it's going to estimate the cardinality in each bucket. And at the end, it will do a harmonic mean to get a much better estimate. So this, let's say this is your hash. This part of the hash say which bucket should I update, and this part of the hash is going to say how many leading zeros are there, right? And if I do that, we get a much better cardinality estimation, and this is the main workings behind hyperlog algorithm. The nice thing about this algorithm is it has really low space requirements. So just by using some like 10 kilobytes, you can estimate cardinality on millions, billions of rows. So it's very practical in that sense. And the error margin is also very low. So for determining, let's say, this type of things, where how large should my hash table be, it's like the perfect algorithm for such applications. So what we do is, when we have our logical plan, and we see a group by where this thing is going to be useful, we do an injection of this hyperlog log when we generate our physical plan. So in our physical plan, we are going to inject the hyperlog log estimation just below the group by. So the entire result is going to be materialized. We will have a perfect cardinality estimation for each partition. And then the group by algorithm will size its hash tables perfectly using that cardinality estimation. There is one caveat. There is, I mentioned this is a simple algorithm, not too expensive, but still there is some overhead of calculating these hashes, right? So if we have perfect stats, then we don't need to do this. And this is a cost-based decision that we also do. If we see that we have perfect stats for this node before execution, then we say, okay, let's not do it. It's not necessary to do this over here. So this is one innovation that we had to do at Lakehouse scale to reduce the chances of OOMs, improve performance significantly. For certain queries, for instance, TPCH Q18 really needs this optimization to work nicely. Yes?
So does that mean the hyperlog log needs to see all the data before you even start looping?
Correct. Yeah. And this is in fact what happens. Okay, now let me move on to another optimization that we did. So I talked about Bloom filters in my previous talk, right? I also briefly mentioned there is this difficulty of Bloom filter sharing. So we have, let's say, hundreds of nodes, right? And we decide to do a system partitioning join. That means each node is going to build their local Bloom filters. Now they need to merge them somehow to create a global Bloom. So the question becomes now, how do we share, right? How do we do this reduce operation? Before Lakehouse scale, we used to do something inefficient, but it turned out to be not too big of a deal because we had like not too many nodes, right? So each node was doing a broadcast of its local Bloom filter, and then we finally each node gets all the copies, and we do a final merge locally. So what is the cost of that? If we do a back of the envelope, the broadcast cost is 2 times. Why 2? Because we need to send and receive. And then the Bloom filter size multiplied with the number of nodes divided by the network bandwidth. Right? So if we assume, for instance, Bloom filter size is 4 gigabytes, and if we assume we have 512 nodes, this becomes 68 minutes. So really more than an hour, really long time, right? So for this scale, we really needed to optimize this process. we can do something much smarter actually. Instead of doing a broadcast, we can do a binary merge, right? So how this works is we perform number of rounds, and at each round, the Bloom filter is sent to the neighbor, right? So at the first round, it is sent to the next immediate neighbor. In the round following that, it is sent to the power of 2 of that round neighbor, right? So as an example, round 0, it's sent to the 1 modulo n, n is the number of nodes, neighbor, and then the next round 2, and then the next round 4, like power of 2 always. And as you can see, the number of rounds that we need to do is log n actually, n being the number of nodes. So the cost, if you look at the cost again, now instead of multiplying with the number of nodes here, we multiply with log 2 nodes. So this becomes log 2 complexity operation, and we reduce the time from 68 minutes to just 72 seconds. So this is again an optimization that we did. And so the excerpt that I'm showing here is TPCH query 21. For this, it's really necessary to do this optimization, otherwise the query runtime was too high. Okay, so let me talk about another optimization. So we call this late decompression. What happens in Lakehouse and also in Warehouse actually, when we load, when we ingest this data, we compress it, right? So it's heavily compressed, mainly using LZ4 compression algorithm. And we recently actually introduced an adaptive compression method where for different column types, we might use run length encoding or the other P4 encoding algorithm to compress data. So we compress data, and while processing the query, we need to decompress it naturally, right? So the question is, can we avoid decompression for rows that we are not going to need for the result? And this is indeed the case. If you have, let's say, some filter on the columns, and it turns out the filter is eliminating everything in some portion of the data, you do not need to decompress it, right? Or if we have even a Bloom filter, some filter that we generate internally, again, we can do the same optimization. We do not need to decompress data if entire portions of the data are being eliminated. And here, what I'm showing is a join between line item and some other table. And here on the line item table, we have a Bloom filter apply, where we need to look up L part key. So that is the only column that we need to do this lookup. But the query might project other columns as well. So in this case, we decompress only that column and do the lookup. And if it turns out that the lookup returns 0 rows, we can skip decompressing other columns, right? So this gives us quite an advantage. For instance, in this case, runtime savings 3.1 seconds, from 6.9 seconds down to 3.8 seconds, just by skipping the unnecessary decompression. Just to give you an implementation sketch, it doesn't have to be a Bloom filter, it can be another filter as well in your SQL query. So let's say you do select A1, A2, A3, where A1 is less than 10. Instead of performing these operators, let's say scan, filter, project, at the scan phase we do the decompression on all the columns. So this is the baseline, this is the expensive part. So we modify our query plan to do something like this. So we decompress only the columns that we need for the filter evaluation. We do the filter and we produce a bit vector. If the bit vector contains no bits, then we can basically skip the decompression. Otherwise, the bit vector tells us that we need to decompress data, and this is done at a later point. So this is called late decompression. See, I have some more minutes. Another thing that we did for the Lakehouse scale is implement a barrier. So why was this necessary? So in the Lakehouse scale, when you have hundreds of nodes, it's very likely that you have some straggler nodes, right? And if we do a system partitioning, and imagine you have a very slow node, that node is going to start receiving data from other nodes, and it's not going to be able to produce data and consume data as fast as the other nodes. So in the worst case, its memory, utilization locally will be 2x because it's not able to consume its local data and it's receiving data from other nodes. So in this case, it increases the chances of hitting OM failures quite drastically, especially in scale. So what we have to do is basically implement a barrier. Whenever we have a system partitioning node, we implement a barrier. So all the nodes wait until we reach that barrier, and only then they start sending data. This reduces the chances of hitting OM significantly. Yeah.
So that's because between the nodes, excuse me, between the nodes previously you sent stuff and the receiver will always receive it.
Yes.
And that basically and now you said, okay, I can't receive it, I'll wait. And the guy has to wait for me to finish and then pass things on.
Correct. Yes. This becomes especially a problem if you have very deep query plans, and then at the end, if you don't have any barriers, some of the nodes might reach the end stages of the query while the other ones are still at the bottom. So then it becomes a really necessary thing. I think the final one that I will talk about. So we have something called task scheduling. So what this means is, in this physical plan, each of these nodes that you see are actually so-called tasks, and we can schedule them at compile time. For instance, an eager scheduling algorithm determines all the subtrees that send data to the network and schedules them first. So here, for instance, all these leaf portions that you see are portions that produce data to the network. So we schedule them first in our execution plan such that we can overlap network time with execution time as much as possible. But as you can see, if we do that, we will have high memory consumption. Lots of intermediate relation data will wait in the memory. This might increase the chances of hitting OL. So what we have implemented is basically, at compile time, we try to estimate how much memory will each subtree consume, we do eager scheduling only until we hit some threshold. Above that threshold, we switch to conservative mode, where we do not do this eager scheduling. Right? We try to reduce data as much as possible. So, for instance, we schedule joins that will reduce the amount of data first. We schedule filters that will reduce the amount of data first. So this is some compilation tricks that we had to do to achieve good performance and reduce the chances of OL. So all these optimizations basically culminate in the fact that with Lakehouse we can achieve the same performance as Warehouse. Right? So it doesn't matter whether your data comes from InnoDB or whether it comes from Object Store. We are ensuring that the performance is going to be the same. And in fact, some of these optimizations that we did even improve the warehouse field. So this was a nice addition, basically. Okay, to summarize, I talked about Lakehouse end-to-end workflow, how we ingest tables. I talked about how we parallelize data ingestion, so how we achieve robust parallelism while doing intra-file processing. And then I talked about query optimizations, adaptive execution, doing efficient Bloom filter sharing while doing binary merge, late decompression, network barriers, and memory-aware task scheduling. So if you have any questions, I'll be happy to take them. Thank you.